In lesson 3 of labor market discrimination, chapter 9, we're going to test whether promotion and race are dependent events. And if we conclude that they're dependent events, then that's a red flag. We needed to look a little deeper and see if that those differences, the dependency, is discrimination. So in order to do this, we're going to copy the data at the bottom of this problem to Excel, so that employee ID is in cell A1. Then we're going to use the mouse to select all cells that contain variable names and the numbers below these names. Okay, so let's go down here and grab all that data. The employee ID number is not a variable. It is a synonym for the person's last and first name. Numerically, those numbers have no meaning, right? So counting the averaging them or calculating the standard deviation from them is ridiculous, right? So notice I right-clicked and saved and then chose match destination formatting. That deletes any that would delete any HTML code in this copy, right? It only pastes in the values in the cells, not the table structure, right? Okay, so then I'm going to expand that and I'm going to center it. Okay, and then I'm going to highlight all the data, make sure all the data is highlighted. Okay, I got an S there from the word submit. So I'm going to make sure all this data is highlighted. The instructions say to create a pivot table, right? So we're going to go to Insert, Tables, Pivot Table, from Table Range. And I'm going to pull this over here like this. Okay, so that's good. The table range. Make sure it's all highlighted. Make sure the Las Vegas sign is around the data. It is. We're going to put it in the existing worksheet. And we're going to put it at the very top here. I'm going to put it in E1. Then I'm going to click that, and then I'm going to click OK. Now I need to go back to the problem. Race is in rows, and promoted, not promoted is in columns. So I'm going to drag race into the rows area. I'm going to drag status into the columns. And I got not promoted and promoted. Then I got black and white. So that order is correct. And this order is correct, right? And then if I drag employee ID into here, because employee ID is recognized as numbers, it does sums, right? It does sums. See that? So I want counts, right? I want counts. So I can click on this down here. Whoops. Value field settings, and I can change it to count, right? Then I get the count instead, right? Or instead of using value, instead of using that, I could have just used either one of these two, right? Either one of these two are categorical variables, and I could use that, and this default is count, right? So you got to be really careful when you have something like employee ID, right? It'll want to sum, right, by default, because it recognizes it as numbers. Use the values in the pivot table to fill in the table below, and they're gonna answer the questions, right? So the number of black and not promoted is 55. The number of black and promoted is 17. The total number of black employees at the company being considered for promotion is 72. White and not promoted is 89. White and promoted is 48. Your numbers are going to be different than mine, right? And then the total number of employees considered for promotion is 137. The total not promoted is 144. the total promoted is 65, and the overall total is 209. So if I add these two together, I get 209. If I add this and that, I get 209. If I add these four, I get 209, right? Now we've used the numbers up here in this table to answer these questions down here. So 209 right here is the number of employees that are considered for promotion, right? Because 144 were not promoted and 65 were promoted. So that's 209, right? And then 144 is the number of employees that were not promoted, the total of this column. And then 137 is the total number of white employees considered for promotion. 89 weren't promoted, 48 weren't promoted. How many employees are white and not promoted? Well, that was 89, right? Not promoted and white, 89. How many employees are black and promoted? And promoted, right? That's 17. We have black applicants who are considered for promotion. 55 were not promoted, 17 were promoted, right? Now we got to calculate the probability of an employee being promoted. The probability P of parenthesis, P, the second P inside the parentheses means promoted, close parenthesis. The probability of promoted equals what? Well, to get the probability of promoted, we take the 65 and we divide that by the 209. And then we reduce the number of decimal places to 4, right? So the probability of being promoted is 0.3110, right? Now we want to calculate the probability an employee being promoted given that the employee is black, right? So we're going to change this probability of promoted to probability of promoted given the employee is black, right? In order to calculate this probability, we have to take the number of employees who are promoted and divide that by the number of those black employees that were considered for promotion, in this case, 72. And we get to 4 decimal places, 0.2361. Now, these two things are different. And because they're different, the two events are considered dependent events. So in probability theory, if these two probabilities, they're both probabilities of being promoted. One's the probability that an employee is promoted. One's the probability of being promoted given that employee is black. They're both probabilities of promoted. Let's calculate the probability of promotion given white. So we're going to change this B to a W. And then we're going to do equal, how many white employees are promoted? 48. How many white employees are there? 137. And what I'm going to do now is I'm going to put the probability of promoted in between the two. If promotion depend on white, this would be 0.3110 and this would be 0.3110, right? They'd all be the same value. So you can think of this as an average of those two. Not, a straight up average where you just add them together and divide by 2, right? If I add these two together here, I get an average of 0.2932, which is close to the probability of promoted. But it's not an equal weighting average, right? Because there's a lot more whites at the company than black people, right? This is the weighted average of that and this, right? If these were all identical, we would say that race and promotion are independent, but that's not the case, right? Black and promoted are not mutually exclusive events, right? There's an intersection, right? If this were 0, then we would say mutually exclusive. But this is not 0, so we can say they're not mutually exclusive, right? In this example, there isn't a third category here, right? Maybe the third category would be black and white. My kids are black and white. My wife is black, I'm white, right? But in this example, we don't have a third category. So you're either in the black category or in the white category, right? So in this example, we're saying that black and white are mutually exclusive. Okay, so now we're going to do a statistical test. And the statistical test we're going to do is based on this definition of probability of promoted given black. Now, I have it written a little differently here. The probability of promoted given black is equal to the probability of promoted and black divided by the probability of black. So what I've done here is I've multiplied both sides of this equation by the probability of black to move the probability of black over here, right? And one thing to note here is we got the probability of promoted here, right? And we got the probability of black here. Here we have the probability of promoted given black. And here we have the probability of black, right? So if promotion and race are independent, this probability here would equal that probability there. So this equal sign here assumes independent, right? This equal sign here, not that one. This equal sign, this one on the left, assumes that the promotion and race are independent, right? This equal sign here is from the definition of the probability of a promotion given black. Okay, so what I'm doing here is I'm getting rid of the center term, right? So again, this assumes independence. This assumes independence. Okay, now the probability of promoted is just the number promoted divided by the overall total. The probability of black is the number of black employees divided by the overall total. The probability of promotion given black, so this is the number promoted and the number black, and divided by black employees considered for promotion, right? So I can calculate this using these frequencies. And then this right here is the probability of black, right? The total number of black employees considered for promotion divided by the overall total. Now, notice that these two numbers cancel here. So if I multiply both sides by t, right? If I put a t here and I put a t over here, this t and one of these t's cancel, right? So I end up with number promoted times the number of black employees considered for promotion divided by the overall total. And because I multiplied this side by t, these two t's are gone, right? And these two b's are gone. So this is the number of promoted and black, right? This is the promoted and black. So this is what we observe, right? This is what we observe. And this is what we expect, right? This is what we expect. If what we expect equals what we observe, then we have independence. These two are identical, we have independence. If these two are not equal, if they're different, we have dependence. And so this P here is a row total, and this B here is a column total, and this is the overall total, right? Now, this right here is the foundation of this chi-squared test that we're going to do, right? So the left-hand side is the expected frequency, while the right-hand side is the observed frequency, right? And we're assuming, again, that they're equal. So we're operating under the assumption that we have identical values, and identical values imply independence, right? So the null hypothesis is promotion and race are independent events, right? And the alternative hypothesis is promotion and race are dependent events, right? Okay, so now we got to calculate the expected frequencies, right? The expected frequencies here. So I'm going to delete this. I'm going to copy this stuff down here. I'm going to get rid of all the extra stuff that I don't need. Okay. I'm going to put these on the left. I'm going to reduce the number of decimal places to 0. Okay, so these are my observed frequencies, right? I'm going to put them in a box. I'm going to copy this and make a copy of it down here, right? I'm going to delete the values inside. Okay. Now I'm going to use this right here to calculate my expected frequencies, right? These are the observed frequencies. The P and B, they're the 4 observed frequencies, right? This is P and B. This is P and white, P and B, P and W, N and B, N and white. So these are the 4 observed frequencies. Now I got to calculate the expected frequencies, right? So the expected frequencies are the row total, right? The row total times the column total. And then I want to divide by the overall total, right? The overall total. Okay. Now this 50 is pretty close to the 55, right? It's not too far off. There's a difference, right? And we expect that difference because that's what we found up here, right? These two values were different. So we expect differences, right? Now, in data that is naturally hatched in the environment, when it's hatched naturally in the environment, the probability that these two things are going to be equal to 0 is going to be 0, right? We expect there to be differences. The question is, are those differences significant or insignificant? Insignificant differences implies that there really isn't any dependency here, right? Significant differences, you know, they overcome the benefit of the doubt, right? And we can conclude that there is a dependency, right? So let's calculate the next one. So on this next one, we have the row total, right, times the column total divided by the overall total, right? And we get 22. 22 is pretty close to 17, right? They're pretty close. Now, are these integers? No, they're not integers, right? Okay, so now we got to do the expected frequencies for white. So we're going to do the total number of white, the row total, times the column total, not promoted, divided by the overall total. And we get 94.923. And it's, again, pretty close to 89, right? It's not too far off. They aren't too big of differences, right? Now let's do the total white, the row total, times the column total promoted, right? When we multiply, remember, multiplication in probability theory is and, right? Then we divide that by the overall total. And 42 is kind of close to 48, right? Now I've copied and pasted them into here, right? See that? If these are the expected frequencies, right? And these are expected frequencies for the white employees who are considered for promotion. Then these two things should sum, right, to 72, and they do, right? And let's just change the number of decimal places to make sure, right? So I'm going to pull this down. Yep, sure enough, those two add up to 137, right? And then we'll add these two together. And those two, sure enough, add up to 144, right? And then these two should add up to 65, right? All right, when I entered in these row totals and these column totals and the overall total, I got green check mark, just as expected. Now to calculate the chi-square statistic, I need to subtract the observed frequency for a column in a row, not promoted in black, for example. So this is not promoted and black observed frequency, which would be 55, minus what we expect it to be, 49.6077, if the events are independent, right? And we square that and we divide by the expected frequency, right? So to calculate the chi-square statistic, I need to calculate 4 of those. One for each of these up here, right? One for each of these pairs. So over here, I'm going to take the observed frequency 55 for the first row and the first column, not promoted in black. I'm going to subtract off what we expect it to be, right? And I have I don't know if that's a small difference, but the difference is 5. And then then I got 4 of these differences, right? So they're all the same number, but 2 of them are positive and 2 of them are negative, right? And your numbers are going to be different than mine, right? So these are the individual differences, and the individual differences imply there is a difference. So these non-zero differences are saying that being promoted or not depends on being black or not, right? So that's what these differences are saying. But again, with data that is birth in nature, we can't expect these differences to be 0, right? So what we're looking for is, are these 4 differences collectively significant or insignificant? In order to do that, we have to calculate the chi-square statistic. So what that involves is squaring these values first, right? To get rid of the negative signs, right? We want to get rid of the negative signs. And then we have to we have to make them relative. We have to make these squared deviations relative to their expected frequency, right? So I'm going to divide each of these by their expected frequencies, right? And the result are smaller numbers, right? So I'll go ahead and enter these in. Let's go over and hit enter to make sure we got it right. And it looks like we have. Now we got to calculate the chi-square statistic, right? And the chi-square statistic is just the sum of these 4 things, right? So the chi-square statistic is the collective differences, right? The collective differences. And it's only 2.8752. Now, the degrees of freedom of this test is, right, we have 2 columns up here. We have promoted, not promoted, 2 categories in the columns. We have 2 categories in the rows, black, white. So the degrees of freedom is the number of columns minus 1 times the number of rows minus 1. So 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. So the degrees of freedom of this thing is 1. Okay, so this is the chi-square statistic, the test statistic. The test stat. This is the degrees of freedom. And then you have the p-value of the test statistic, right? So this is 1. Now, to illustrate how this works, I'm going to pull up a website that you might be familiar with at this point. If you take my stats class, you are. I'm going to pull up a website called statdistributions.com. And I'm going to click on the chi-square one. I want the chi-square distribution. I'm going to change the degrees of freedom to 1. And then I'm going to change the chi-square value to the test statistic value right here, right? 2.8752. So 2.8752. I can't do 4 decimal places, so I had to stop at 3. Okay, so the p-value is kind of large, 0.09, right? The p-value is the probability of being to the right of the chi-square statistic, right? So that's the p-value. The probability of being greater than the chi-square statistic is 0.09. Now, to get the p-value in Excel, we type equal chi, right, square, and I have a bunch of choices here. I got chi-square.dist, I got chi-square.dist.rt. Notice this is the right tail of the distribution, right? So I'm going to click on chi-square.dist.rt. It's asking for a number on the number line, not an area under the curve. So I'm going to click on the test statistic here, and then I'm going to hit comma, and then I'm going to click on the degrees of freedom, which is 1, right? And then I'm going to close the parentheses and hit enter. So the p-value to 4 decimal place is, in fact, 0.09, right? The p-value is, in fact, 0.09. So it agrees with statdistributions.com. Now, the test is being conducted at the 1% level. So this is the significance level. And the significance level is the alpha level, right? So well, we can type 1%, right? And then we can convert it to a number, right? To 4 decimal places, right? So that's 1%. That's the significance level, right? Now we need the critical value. So you can get the critical value in statdistributions.com, right? I'm going to change the p-value to 0.01. And notice the chi-square statistic is the chi-square value is out here at 6.617. That is the critical value, right? The critical value looks to be larger than the test statistic, right? Now, this might not be very accurate, right? We expect it to be 6.617, right? I'm going to, instead of using the value from statdistributions.com, I'm going to type equal chi square, right? Now, .dist.rt feeds in a number from the number line, which was a test statistic, right? Instead of using .dist, I'm going to use .inverse, .inv, .rt, because it's a right-tailed test. Now it wants an area under the curve called a probability. The area under the curve is my significance level 0.01. And then comma, the degrees of freedom. So the critical value is 6.6349. Here it's 6.617, right? So sometimes statdistributions.com is a little off, right? It's a little off here. So we're going to use the value from Excel for the critical value. Okay. Now, let's go back to statdistributions.com, right? Let me widen this up. The area under the curve that is right at the critical value, this area is called significance, right? And our chi-square test statistic, right? Our chi-square test statistic is a function of the collective differences. Now, if these collective differences, if this function of collective differences was under this blue probability tail, those collective differences would be significant. But our test statistic is over here, right in here somewhere. It's under the white area of the distribution, right? When we're under the white area of the distribution, the collective differences are insignificant. And when the collective differences are insignificant, our conclusion is that it's probably independent. The events are probably independent. So we have evidence in support of the null. Now, if your test statistic that you calculated in Excel was bigger than the critical value, right, that corresponds to the significance level, if your test statistic is up here, that means the collective differences are significant. In that case, you would have evidence in support of the alternative hypothesis, right? And you can accept the alternative hypothesis. You can't accept the null hypothesis. But in my data, the chi-square test statistic is less than the chi-square critical value, which means the collective differences, the function of collective differences, indicates the collective differences are insignificant, right? And so we have evidence in support of the null hypothesis. We can't accept the null. We're not going to reject the null. What we can do is we cannot reject. What we can say is we cannot reject the null hypothesis, right? Which means we're not concluding being promoted depends on race. We're not saying promotions do not depend on race. What we can say is, quote, we cannot say that promotions depend on race, right? Again, we can't accept the null. We can fail to reject the null, right?